Hello, everyone. Hope you had a nice 15-minute break. This is of course, the second morning session of the conference in track 3. Just a quick, I'm George, so we'll be helping with some of the chairing of today's discussion. And for our first speaker of this session, we have Professor Charlie Yang, who's the leader of Robot Teleoperation Group at Bristol Robotics Laboratory. He's a fellow of British Computer Society, an awardee of the EBSRC Innovation Fellowship, and a recipient of the IEEE Transactions on Robotics Best Paper Award. He received his PhD from the National University of Singapore in 2010 and performed postdoctoral research at Imperial College London. His research interest is mainly in human-robot interaction and intelligent system designs. So I'll hand over to him now. If you have any questions, you can put them in the comments section and I will ask them at the end of the session. Okay, over to you, Charlie.
Thank you, George, for the introduction. And it's my pleasure to share with you about my research topic on robot skill learning and human-robot shared control. So yeah, I'm the lead of BRL, Robot Teleoperation Group. Let me take a few minutes to introduce what we do in Teleoperation Group. Basically, we investigate a number of different technologies such as mixed reality and signal processing of muscle electromyography signal and human-robot physical collaboration control system in order to provide immersive user experience to the teleoperator and enhance the performance. For example, we investigate how we can do shared control not only at the master side but also at the remote side. We enable the robot to collaborate with human beings. Yeah, that's what we do in the teleoperation group. Okay, let me start from an example to show about what skills we humans have. For robot control, we have motion control, we have force control, we have impedance control. Most of the time for a simple task, we just do motion control. But for complicated tasks, especially for those tasks with interaction, force interaction with objects, with the environment. For example, if we do cutting, carving, or drilling, for this kind of task, we need to control the force. Not only that, we also need to adapt stiffness of our muscles in order to perform this task properly. So this will lead to the topic of impedance control. And yeah, so how does our human motor system control force and regulate stiffness at the same time? So in a Nature paper published 2001, an experiment has been performed to show that it's a test on human subjects in a force field which is unknown to the human subject before the experiment. And according to the comparative study, the result is that our human motor control systems is able to adapt the end effectors of force and tune the stiffness at the same time independently. That's what this experiment shows us. And another experiment in 2006 also shows that our human motor system is actually performing compliant control according to the interaction force. If in this force field for the experiment, if we increase the virtual stiffness of the force field, we can observe that the human subjects try to be more compliant by adapting the reference trajectory. Because in the catch trial, if you remove the unknown force field, the human subject do not tend to restore back to the straight line motion. Instead, they still go along the curved line. So this, from control point of view, this illustrates the motor control system actually has adapted or have learned the new reference trajectory. According to this experiment, they proposed a learning controller, we define that there is a task trajectory and adaptive reference trajectory, and we can online tune the impedance, feed-forward force, and trajectory at the same time. In order to develop the learning law, we first propose a cost function, and by minimization of that cost function, by using optimal control method, we will be able to derive the control system. It can be our controller can be either used on time domain or can be used on as iterative control. It can be on iteration domain. Yeah, so it is either iterative control or adaptive control. Our controller can be adapted to both versions, and according to our simulation, our algorithm are able to reproduce the motor behavior as observed in the previous experiment. More than that, our algorithm can also be implemented on control system, on robot control system. This video shows us our control system in comparison to the conventional control system, just to show the superior performance. First is about drilling. Yeah, so if you use a conventional fixed controller in comparison to our adaptive controller, you will see our controller perform much better. Another example is the karting. As you can see, our control performance, the karting, you do not damage much of the surface, and you can cut very nicely, similar as the drilling example. Yeah, so this piece of work won the Best Paper Award of Attribute Transaction on Robotics. And in this published paper, we first proposed the human-machine, the concept of human-machine learning cycle. Yeah. Now let's show our research on shared control for teleoperation. So this video shows that we use a joystick to control the arms of the Baxter robot to do a simple pick up and place task. Well, as you can see on the wall, we attach a paper box as obstacles. Yeah, the Baxter's arms elbow may bump into the paper box if you do not do not do obstacle avoidance, as you can see. Because the human operator is focusing on the motion of the end effector, he may not be able to take care of the motion of every joint. So in the first instance, you see the elbow on the right arm of the Baxter robot, yeah, bump into the paper box. If it's a real obstacle, it may damage the robot. Well, our method is that we enable the robot to autonomously avoid the obstacle by the motion in the joint space, while the human operator only concentrates on the motion of the end effector. He does not need to worry about the collision. Yeah, so this can be done because the redundancy, because Baxter robot's arm has 7 degrees of freedom, more than the 6th of Cartesian space. So we have kinematic redundancy. We can use the motion in the so-called null space to do the obstacle avoidance, while the end effector motion will be only controlled by the joystick without any side effect from the obstacle avoidance motion. Yeah, we apply the idea to teleoperation of the surgical robot as well. For surgical robot, it's more complicated. First, you can see the surgical tool attached to the KUKA robot. It is working through a very small hole for the minimum invention surgery. So this small hole actually poses a constraint on the motion of the KUKA robot. And so as usual, there's always some human assistant standby. For example, sometimes this assistant may need to wipe the blood. So he may need more space. He needs to move the robot. So if he interacts with the robot, this actually causes disturbance to the operator on the remote side. So how can they collaborate effectively? Let's see the video. So as you can see on the top left, that's a motion of the tip of the surgical tool inside the hole on the human body phantom. It's not a real human, it's a phantom. As you can see, the tip of the tool track exactly the motion command sent by the master side human operator who uses the Omega 7 joystick. You can track a solenoid, you can track any predefined, for example, any trajectory you predefined in the color of green. At the same time, you can see the assistant is physically interacting with the KUKA robot, but this will not affect the motion from the master side, and will not affect the performance of the surgical tool. So yeah, so in this work, we consider a remote center of motion as a constraint. We also implement the obstacle avoidance using kinematic redundancy. In addition, we also used compliant control to make sure the safety for the physical interaction. And for teleoperation, in addition to the joystick, which can send a motion command to the remote robot, we also consider to use a muscle signal electromyography, which is quite useful because it can provide extra degree of freedom to a human operator to teleoperate a robot. As you can see from this experiment, we did comparative studies. First, we control the robot using a joystick. On the robot side, we set the controller parameters. For example, the proportional gain. We set it to be high, so that the robot will be under the high stiffness mode. And you will see that because when the robot pick up a heavy object, because the sudden change of the dynamics, the whole system becomes unstable. Oscillation happens. And then in the second scenario, we change the controller parameter on the robot to be low gain controller. And you can see in that case, robot may hardly produce enough force to pick up the object. So let's see. At beginning, we use high gain control. You see oscillation, instability happen. And next, if you tune the control parameters to be very low, it cannot produce enough force. So too low or too high, the performance both not good. So what will be the optimal one? So finally, we use our adaptive controller. The controller parameters are actually set by the muscle electromyographic signal from the human teleoperator. Because as we have force feedback to the human operator, when your hand is holding the joystick, you can feel how heavy the object is when the robot pick up it. So when you feel the pulling force on your hand, you have a natural response. You increase your force. So we use a armband to detect the muscle signal, and the detector, when the detector collect the increased muscle activity signals, it will send this information to the robot for the robot to online tune its control parameter. So it's kind of a human in the loop controller. It's like when you drive the cars, you can adjust speed and the direction. So for teleoperation, if you produce this kind of force feedback to the human operator, the muscle activation is a natural response. If you collect this kind of information, this will be very useful to adapt the control parameters on the robot so that the performance can be much improved. And this idea can also be used for human-robot collaboration. For example, we did a test on a collaborative human-robot task for sawing a piece of wood. In this task, we need the robot to provide an assistant to the human operator, for the human co-worker, so that the human operator's effort can be minimized, while at the same time the performance can be maximized. So this involves so-called matching, impedance matching. So the controller on the robot must be matching the control system of the human operator so that they can do the optimal collaboration. Well, how do we do that? We use an optimal controller based on ILQR model, and we also use the armband to collect the muscle activation signal from the human's arm, and we can online estimate the muscle stiffness and the force. Let me show the video on the next page. So usually for this kind of task, we have two humans collaborate with each other, one on each side, while we can replace another partner with a robot. As you can see, we attach a force sensor on the end effector of the box robot, and we do first we test admittance control. So the robot can collaborate with a human factor while you can change the frequency of the motion. You can increase or decrease the range of the motion. Well, that's not enough. We also want the robot to provide optimal assistance. So yeah, we detect the muscle activation using the armband, the white armband, one on the forearm, and we use the signal to online adapt the robot's controller so that the robot can provide best assistance. So in comparison to the fixed control system, from data analysis, we will see that. So first, we can see that the control effort from the human operator is much reduced. That means it makes the life easier for the human partner, and the cutting surface is quite smooth using our controller. Otherwise, you see the cutting surface is not that smooth using the fixed controller, and the human's effort you have to spend more energy to work with the robot if you do not use our adaptive controller. Muscle signal can also be used for controlling a mobile robot. So we propose a new control system to control a mobile omnidirectional mobile robot using a pair of muscle armband. As you can see from the video, the operator wants a pair of armband on left and right arm. On one side, on the left side, it is to control the direction by using hand gesture. On the other side, it is to control the speed. If you stiff up your arm, the robot will move faster. If you relax the arm, it will reduce the speed. Yeah, so this will provide a very good user experience to the teleoperator. He can use 2 arms to control the robot, to tune the speed, and to control the direction.
Next.
And yeah, let me move to the topic of skill learning. So if we interact with the robot, would the robot be able to learn skill from interaction and then take over to do something automatically? That's what we think is something we need to investigate. So in the literature, we can say to model, to represent human skill, or modeling to model the human skill. There are basically 2 methods, either a statistic method or by using a dynamic system. While most of the time in our research, we use the so-called dynamic movement primitives. It's easy to model the skill, but it will be more useful if we can generalize the skill. For example, in this video, we show that if we teach the robot to lift up the bottle of water, when we teach it, it's half a bottle of water. And when the robot needs to do another task, when the bottle is full, it's full bottle of water. If we do not have generalization, the robot may fail the task. On the left side, the video shows something similar. We teach the robot a pick up place to move the blue block into a green cup. To reproduce the motion is quite simple. The robot can exactly do what the human demonstrator taught it to do. While what we want is when things change, when in the new situation, in the new scenario, for example, if you move the green cup from the up corner to the bottom corner, you change the target's location. We say the robot will be able to automatically figure out a new trajectory. You do not need to teach it again. And as you can see from the left video, even if you move the target in the halfway of the motion of the robot, it can online change its trajectory, motion planning, to move to the new target place. And in the task of pick up and place, when we do the teaching by demonstration, we usually segment the motion into a number of phases. For example, for this simple task, you can see we make it 4 different phases. When you approach the bottle, when you pick it up, when you move it over to the obstacle, and then you place it on the go. Why we needed to do segmentation? This is also a quite important research topic for imitation learning. Why we needed to do segmentation when we transfer skills from human to the robot. I will use a video to show you. This video shows we have a Chinese student to teach the KUKA robot to write Chinese characters. So there are more than 10,000 Chinese characters. You cannot teach every Chinese character to the robot. That will be too time consuming. But fortunately, there are very limited number of strokes, just like there are only 26 letters in the alphabetic table, right? So if you can do segmentation, when you teach the robot to write 2 lines, the robot will be able to learn each stroke and recombine to write something new. The first 2 lines were taught by the demonstrator. The next 2 lines were reproduced by the robot without being taught. It just used the strokes learned and recombined them to write something completely new with same written style as the demonstrator. So this is why it is important to do segmentation, because that will be very useful for the further generalization. And most of the time in the literature, most people only consider motion control. While we use this video to show that motion control alone is not enough. If you teach the robot to swipe on the table surface, if you only consider motion to reproduce the motion, you can see it may not do the task properly. And if you teach the robot both motion and force, the robot can follow what it has been taught. So this video shows why it is important to do motion control and force control together. Well, theoretically, force and motion are still not sufficient. We also need to consider stiffness. That's why we proposed a new learning framework. We call it a 3-in-1. We use hidden Markov model to model the correlation between force, position, and stiffness, and we combine these 3 into 1 to transfer the manipulation skill from human demonstrator to the robot. And the stiffness is actually quite hard to measure. We don't have any sensor to measure stiffness, so we build a mapping of the muscle EMG signal and stiffness during the Kelly operation. And later, for the online experiment, we use muscle electromyography to estimate the stiffness. And this video shows our result. So we, at Euro, we did a comparative study. We show that the task may fail if you only consider a force or only consider a motion. Only if you consider force, motion, stiffness altogether, you can successfully reproduce the task, even if you move the location of the button or make it lower. It's a simple task for our human beings, but force control is quite hard for robots, especially if you change the button, you change the location, you make it higher or lower. The robot may not be that intelligent. But by using our method, the robot is able to do it well. Now, finally, I would like to take this opportunity to introduce our recently published monography on robot learning. It's published by the Taylor Francis CRC Prize. And this animation also shows a bimanual manipulation platform we are building in our robot teleoperation group. I hope in the next few months you will be able to see it in BRL. Okay, that's the end of my talk. Thank you very much.
Great, thanks very much, Tori. That was brilliant. We saw a whole raft of applications and indeed a whole load of theory, which all looked well. I found all of those applications particularly interesting. So one of the applications that you spoke about was skill transfer, and you made a big deal within that the I suppose you'd say the stiffness variation helps with the generalizability of skill transfer. Would you say that's the sort of most important, or I guess largest contribution to skill transfer that stiffness variation does, or is there?
Yeah, in comparison to the conventional skill transfer method, that's quite important. We also consider stiffness variation.
Okay. And when it comes to manipulation skills, what are the most in the literature and in your work, what are the most used methods to represent manipulation skills?
We use so-called dynamic movement primitive. It's one of the methods of so-called dynamic system. Basically, you use a differential equation to model the motion skills. Yeah. On the other side, there are also other methods, statistic method using a Gaussian mixed model or hidden Markov model to model the skill. Yeah. Basically, there are two schools of method.
Okay. All right, brilliant. Well, thanks very much for that. I'm sure everyone watching enjoyed that and found that as interesting as I did. So thanks very much, Charlie.
Thank you.
Thanks. I'm waiting one speaker, but so the next talk that we're going to have is a collaboration between, they're both here now. Okay, so the next talk we're going to have is from Rob Clarke and Puneet Chhabra. So Rob Clarke, I had them both. Oops. Yep. So Rob Clarke is currently an RA with the University of Bristol, working on the Prometheus project and focusing on flight control and system integration. And he'll be coming back to the University of Bristol to do a PhD in applications of machine learning to flight control. He's been collaborating with Puneet Chhabra, who is experienced in LiDAR, radar, and sonar technologies, working in academia and industry, and filing multiple patents on signal processing and sensor systems. He's got a PhD in electrical engineering from the Heriot-Watt University, where he specialized in advanced single photon LiDAR and sonar radar technologies. And he's also worked as a higher scientist at the BAE Systems in Filton, Bristol. So I'll hand over to them now to begin their presentation.
Thanks, George. I'm just going to quickly share my screen and start the presentation. There. My screen is frozen. Oh, hang on. There you go.
Sorry, Puneet, could you move your mouth close to the microphone? Perhaps it's a little bit quiet, but we've got your picture, and I think you sound okay. Other than
that, is this good? Any good?
Yeah, that's better. Thanks very much.
Okay, let me see what's going on. There is a lag with my presentation. Sorry, 1 second. Let me just start my screen share again. Okay, go back to it. Seems to be a lag every time I share my screen.
I think we can see your screen okay on the right.
Okay. Yeah, for some reason it won't start the presentation. Let me just try and share my entire screen rather than an application. Maybe that sorts it out. Apologies. Share screen. Entire screen. Okay, how is it now? Whilst I think, okay, instead, I don't want to waste time. It seems to work, but my mouse doesn't. And my keyboard also doesn't work if I go F5. Maybe Rob, if you want to begin in the meantime, while I sort this out, maybe that's the best.
Yeah, sure, can do.
Okay.
So Puneet was going to give sort of an introduction to the project overall. I've sort of got a presentation talking more about actually the sort of the development story to date, but maybe we'll get a sense of what we're trying to do. So project started back in 2019. I joined in the summer. I think the project actually started a couple of months before that. And we started off actually with some training effectively. So as I guess a brief background to the project, we're building a drone capable of going and exploring these underground spaces. And as part of that, actually, it was important for us to be able to go and actually experience those spaces. So Network Rail, who's one of the partners in the project, essentially organized for us to have some training going and dealing with these confined spaces, which actually helps really with, I guess, developing an appreciation for why actually this project is needed. And actually, the hazards that are underground, mainly to do with sort of atmospheric gases, and actually being able to monitor whether you've got enough ventilation, whether you're actually still able to breathe in that environment. And also actually just giving us a sense of familiarization with the sort of mine environment, because outside of Network Rail, effectively nobody on the project had really any experience with actually what those mine environments were like. So actually sort of being able to go there and see what these spaces were going to look like was a really useful part of the project. So we started through then the autumn with doing some initial work looking at exploring the different sensor options we had available. Actually putting some of those on the drones and seeing how they performed in flight, and whether actually the vibrations of flying things sort of affected the sensor outputs, and equally trying with some different computation options as well, and how could we arrange the overall layout of the vehicle and how that worked with our autopilots, and how we were going to actually interface with that with the rest of the system. And then moving on to that, actually some sort of initial work developing concepts. And so I think in the bottom right there is sort of one of the first concepts we came up with in terms of the overall platform and layout of the system. And then sort of culminated in 2019 at the end of that with actually coming here to the BRL and to the flight arena, where we sort of put all the different systems from all the different partners together and actually had a vehicle flying for the first time with all these various systems on board. So capturing data, flying around, doing some waypoint following from some of the work done at Royal Holloway. And then finally moving on to actually do some demonstrations to a group of essentially operational experts from Network Rail. So that included people who were involved in sort of some of the underground mining systems, as well as the sort of the drone operations that Network Rail is doing at the moment. Obviously, the drone operations we're looking at doing here are sort of quite different from a lot of the drone operations that Network Rail does. So Penny, if you're back, I don't know if you wanted to sort of start going over your introduction to things. Yeah, okay.
Hold on, Penny. I think you've muted yourself quickly.
Apologies.
Yep, there you go.
Okay, I'm back. Yeah, the way I've got structured this is initial intro and headline, and I'm going to skim through this very, very quick, and then give a very brief intro on how Prometheus got started, and then let Rob go through some of the development going from simulations to lab to actually real world. In terms of what headlights, our focus is primarily to sort of refocus on infrastructure that is really aging, and this involves mines, voids, utility assets, which are all sort of subsurface, underground. With the climate change, there is a huge pressure on these assets, and these needs to be digitalized, and you need digitizing technologies that can also sort of move us in the direction of digitization. Our mission is to basically help organizations manage their infrastructure, which involves inspection, mapping them, localizing them, both above and below ground, and ideally in any kind of weather condition. This has got you'll basically see across a spectrum of various utilities, going from water, wastewater, which are quite deep assets, quite underground. In the past, they've been very difficult to access. You got to put men down there, and it's really health and safety hazard. But you have shallow assets, which are electrical supplies, communication networks, recently transportation, but also you have building foundations that go deep, and you've got mining, which primarily is where Prometheus is focusing on. So if you're going to build new infrastructure, these have to be sort of mapped out accurately. So that's a big challenge. This obviously has to be addressed on the UN sustainability goals, and so it sort of overlaps with that. Just to give you a sense of the problem, every minute, again, on the statistics, a construction company does hit an underground utility. This also involves the railway. So you've got more than 5,000 sort of abandoned mines under the railway network. And you got injuries, you got issues with fines, there's a huge cost involved, and you got major delays to projects. So again, it has a huge impact on the economy as well. Roughly, if you want to put men down, it's roughly 20k per kilometer, and that's a massive cost. Again, when we were on Prometheus, one of the motivations was when we started speaking with Network Rail, we kind of saw the correlations between the cost and the safety side. Again, challenges are you got GPS denied, you got to have accurate localization methods, and you have to manage your risks. Again, access is limited in certain situations. That's where you'll actually see how Prometheus helps us to sort of deploy through a very tiny hole compared to actually drilling massive holes. Headlight, we had a team of 6 at the moment, and got combined 70 years, but we've also worked in defense and high-tech industry, so kind of a varied spectrum. Key personnels, we've got Ujar, who has got a PhD in aerospace from Bristol Robotics lab, is all involved on Prometheus. He works very closely with Rob, and then you've got Susanna, who's also managing the Prometheus project, and Jamil and myself are the sort of project leads and finance leads. Just quickly on apart from Prometheus, what actually we have also developed is a product called Telesto. It's commercially available, it's out there, and it's basically improved safety, speed, and assurances on understanding where the assets are, provide you with 3D high def video, and also everything is digitized, so you've got a database, a data platform that you can sort of visualize your assets in. I'm not going to bore you through what this does, but just some images of what actually Prometheus does. So it's deployed through a sort of a robotic platform. It could be a boat or a robot. You kind of do the analysis on the data once the data is collected. And behind the scenes, there's a lot of sensor fusion, SLAM, that help us build these kind of point clouds. We don't make use of 3D LiDARs, especially because of power constraints. So it's all sort of done using multiple 2D LiDARs and cameras. You got the dashboard, and you got accurate localization of where these assets are. Again, what we build on is we're building IP, doing some AI, but at the same time, we're making use of a technology called KX, which helps us to do sort of real-time querying on really massive databases. So that's the kind of things, how we brought things together. A couple of slides just to show you some examples. Again, this was a culvert completely out of shape. The earth above was actually pushing the whole culvert inwards, and there was a huge issue, lots of cracks, pitch dark environment. So sort of we put through Telesto from one end to the other, and we do the analysis on the deformations and things like that. This one here has got lots and lots of infiltration points. So you got root ingrowth, and those needs to be pulled out. So again, identifying those anomalies as a function of distance is quite ideal. So the technologies that are sort of behind this has also been sort of made use of within Prometheus. So again, this is how do we correlate CCTV or video with point cloud, and that sort of helps us. This was 8 kilometers of an asset in Bournemouth, so quite a useful one. Some AI, which might be quite relevant to some of the audience. We try and build and understand what is the material composition, what's the structure. Here we're looking at calcified areas versus exposed aggregate, and these over time build up and cause huge issues to the asset underground. Here's one more example of actually accurately connecting above and below ground, which has been very difficult in the past for longer distances. And Telesto helps us do that with some of the SLAM technology. Again, this is how this image shows how we've connected an underground asset with the above ground. A quick video to show you once you've done that, then through the dashboards, users can start annotating this data and creating taking screenshots or fly through videos and generating the reports that they need. I'm going to talk about now Prometheus. So where this started in around October 2018, and this was the actual original team that got together. Main guy here is Neil Rushton from Network Rail, who presented his challenge that he wanted to map out these mines that could be interconnected through a 150 millimeter borehole. And then we have Simon, Sarah, and Tom from Manchester, Royal Holloway, and Bristol, who sort of brought together the key pieces of the technology. And the main issue is, as I mentioned briefly, you've got 5,000 or more of these subterranean mines, and these need to be inspected. It's a huge amount of money that cost, and a big risk to men and women who actually go down, and we want to avoid that. Ideally, they put sort of sensing pods on a tether system or a pole, but that kind of leaves out a lot of unexplored regions. And what Prometheus tends to do, and Rob will touch in more detail, is we want to deploy it through a tiny borehole, and the drone can then map around and explore the unknown areas as well. What is integral to this is three main innovations. One is the drone design. Again, I'll leave that to Rob. But we got the 3D imaging solution that we've been working on, and we have Royal Holloway, who's primarily looking at the planner side, and we help with some of the localization using the sensing pod. So very quickly, so some of the examples, this is Bristol Robotics Lab, initial trials of the time of flight sensing pod. This is very, very lightweight, under 150 grams. And it's got a surround view, sort of 360 surround view, gives you infrared images and a 3D point cloud. This obviously has to be fused, and that's where some of the SLAM technology comes in. I'll show you a very quick example of what the actual images and the point cloud looks like from the sensors. So these are I'm just showing you the 7 camera systems here, and the point cloud on the right hand side. And again, this has to be obviously you don't have to sort of fuse this information. Once you've done that and you post-process the data, then this is how the sort of the final outcome looks like. And this is like a small corridor section that connects to the main chamber of the mine. And again, this was sort of the data was collected using the sensor, and we sort of post-process it. I think from in terms of the planner and the reconfigurable drone aspects, I'll leave that to Rob to touch a bit. I think he's got a couple of videos on the planner as well, and then I can present you with 1 or 2 videos in the end of the actual flight of the drone as well. So back to you, Rob, if you want to sort of continue with some of the slides.
Yeah, sure. So I already spoke a bit, I say, about the original development we had in 2019, and from that we had a pretty clear plan of what we were going to go into in 2020. So that was actually developing a mock platform that we could use to sort of put together quickly and actually start testing out both the software and actually some of our choices in terms of the electronics, so the powertrain that's actually helping to fly the vehicle, and also develop and test some of the software initially here at the flight arena at the BRL, and then be able to then take that out into field testing. However, there was an event early in 2020 that did sort of change those plans. So we ended up actually doing a lot of simulation development. And in hindsight, that's actually been incredibly useful in terms of the ability for different partners in different locations to be able to sort of collaborate on that simulation. We ended up with the mock platform and the prototype vehicle sort of arriving pretty much at the same time. So there's probably some development sort of has been done unnecessarily on the prototype that we probably could have learned some lessons from on the mock vehicle first. And equally, our field testing schedule has sort of been pushed back, which is actually then hampered by the fact that the site we've been doing most of our field testing at actually has bats that nest in it. So actually over the winter period, the bats are hibernating in that mine, and we're then not able to use that for testing because of bat protection laws. So for the simulation setup, we actually, effectively building on the work of the communities that have built ROS and Gazebo and PX4, there was actually a lot of the infrastructure already in place for us to essentially be able to plug and play between the two systems. So what we ended up with in the end is a system where we had a software in the loop simulator of our flight controller. So that was effectively running exactly the same software that we were running on the real vehicle, sitting within a gazebo simulation. And then we developed a plugin to effectively simulate the Dragonfly sensor and get us that camera data back. So we then have the same interface between the real world and sort of the rest of our code as we did just in the simulator and the rest of our code, which actually made the transfer between simulation and reality really quite easy. And then just in the bottom left there, we've sort of got these point cloud images that were point cloud setups that were provided to us by Network Rail. So actually we're sort of able to test in effectively as close to a real environment as we can, purely in simulation. And then also sort of defining some nice interfaces between the partners, being able to use ROS and sort of things like action lib within ROS actually made those interfaces nice and clear and has made that collaboration relatively seamless. Oh, there we go, it jumps, look at that. We also, as part of our sort of restricted access into the real life environment, we actually sort of built a cave simulator here in the BRL, which is effectively just a set of cardboard wooden boxes which are designed to, they restrict the airflow and so actually give you an aerodynamic environment, at least, that it's similar to the flying in the caves. So these do sort of represent the lower limit of feasibility for flying this sort of scale of drone, but it has got a good realistic sort of head crouching stoop when you're trying to walk through them. So as part of the sort of the collaboration between simulator and the real world, I thought I'd just show you this, which is from, this is a planning setup from Raw Holloway. So Raw Holloway put together this scenario. They then effectively ran the simulator to plan a route through the scenario. So we told them this is how big the boxes are. Ali over at Raw Holloway then sort of put the boxes together within this sort of simulated room, gave the planner some goal states, and the planner returned then a path to us, which effectively just, it was gamed such that you'd fly the drone through the tunnel. And we then took that, again here at the BRL, took that into the real world, and were able to then effectively just execute that path in the real world and demonstrate that actually we're able to do that transfer between simulation and reality quite nicely. What you will notice is actually as it goes through the tunnel, unlike the simulated drone, which just smoothly glides through there is a lot of jostling around, and that is most of the aerodynamic effects. So the vortices or the downdraft that the drone is creating are then sort of circling back around, bouncing back onto the drone, and causing a lot of instabilities there. So yeah, I think this is sort of the lower limit of feasibility with this scale of drone, at least, that we're able to fly. We were flying some of the smaller Mavic Minis in some of the field testing, and those are, because they're lightweight, they produce less downdraft, they're able to fit through smaller spaces. The other important aspect is actually the docking process as well. And so obviously for deploying from a borehole, we can't just sort of take off from the ground. So actually the solution we've gone with is to detach from the sort of this docking mechanism. And again, we've built one of these in simulation. So we had, again, a custom plugin built for Gazebo that would enable us to do effectively simulate the grabbing of the dock. And then this then runs the same software that we're running in the real world in terms of using April tags to track where the dock is, using a simulated camera to do the tracking. And then actually we run through this docking process where the drone sort of aligns underneath the dock, starts flying up towards it. And actually, if we watch this, what you'll see is that the initial dock process fails. So in the simulator, that's effectively just because it's misaligned. And the vehicle then sort of goes down into this missed approach procedure and then comes back up and actually manages to successfully dock. And what was quite nice as well was actually being able to see that play out in the real world as well. So what we have here is, again, back in the BRL, we built a sort of a simulated frame for the dock. So rather than actually having us coming out of the bottom of the borehole, we've instead just built this dock that sits on a frame. And then we've got the drone again, detaching from the dock. It sits here, hovers, again, running exactly the same software that was running in that simulator just then, aligns itself beneath the dock, and then actually begins doing the approach process back up towards the dock. And what was actually really quite nice to see was that actually the behavior in the real world sort of mirrored that in the simulation. There was effectively a failure for the the system to detect whether it was properly attached in the dock or not. And so actually it did go into that go around routine again, and before coming back and making the docking process. So I think if you watch here, it will clunk down out of the dock, which I think is some of the pins effectively failing to engage. At that point, the vehicle decides, okay, we're going to abandon this attempt to dock, and backs off and tries again. So I think with that, I will let Puneet take over again in the last 2 minutes, 1 minute we've got left.
Thanks, Rob. I think what I'm going to present is a video of the undocking from an actual in a live environment. This was one of the most recent trials that were done in a real mine at Snail Beach, this is just showing you some of the the unfolding of the drone. It's actually got the sensor, the Dragonfly sensor, and this is sort of showing you how it's going to do the unfolding on a rig, which is kind of a simulation of an actual borehole at the end of it. And this one, this is the same. This shows you the automated undocking in that environment. Again, what Rob has shown you just before this actually completes the story in that sense, in terms of the docking, which is really nice to see, going from simulation to real world. And I think that's very difficult to do, as a lot of people will appreciate, but doing that in a real environment has its own challenges. So we've got what's coming up is we've got a set of trials happening in under a week's time, and then we've got another one after that. And at the end of the month, we have one in Cornwall, which is we were going to actually deploy the drone through a real borehole, which is of the size 150 millimeters. Key personnel from the universities are the PIs, and we just put their contact details there. There was just one more video that I wanted to play. If you this one. This is from the integration test 3, which is in a real mine, and the fly through of the point cloud that I showed you from the Dragonfly was this tunnel where you see the rail, and this is just demonstrating how the autonomous sort of takeoff and flying and then landing. Again, there's more to come, and obviously Rob, Liam, and some of the other guys are actually working on some of the trials and testing BRL right as we speak. So they're doing that. Just going back. So what I think what I'll be looking at, I mean, personally, I'm very much interested in collaborating, and I will be very keen to hear from people what they think about the project and how we can potentially improve it, or if they're keen on collaborating. Autonomy and path blending, there's still a long way to go, so that's another focus of us for phase 2. But the miniaturization of the aspects of the drone, as well as streamlining some of the design, is also the focus of phase 2, which we are already have started some of our work on that, and that could be potentially through grants or through private investment that we are raising at the moment. So with that, I think that's kind of, I want to bring it to a close, and hopefully that gives you a flavor of how we are coming together from an industry perspective, but also have the end user with us, which has been absolutely great, because we are developing something which there is a huge need, and potentially can reduce the risks to human life. So that's it's really good to see that. So yeah, thank you. And any questions? If you have any time for questions, happy.
Great. All right. Thanks. I think we've got a little bit less than a minute left, so I'm going to ask one quick question, but maybe it's just a sort of yes/no answer.
Okay.
So that was sort of a good, interesting application, and indeed a good example of a collaboration for a project that looks very interesting. So drones flying in caves isn't exactly what I'd imagine to be a typical approach, because obviously we imagine drones in open air. And one difficulty that I might expect you to come across is maintaining communication. Indeed, just, you know, if you go down into a cave, you lose phone signal. Is maintaining control, maintaining communication with a drone in a cave a big problem?
Yeah, so essentially we did some testing in one of the initial trials where we're saying that basically as soon as you go around a corner, you've lost all the signal. So the vehicle's been designed effectively from the start to be completely autonomous. So we send it off and hope that it comes back.
Right. Okay. All right. Great. Well, as I said, we're going to move on to the next speakers now. So thank you too. That was an interesting talk. Thanks so much.
Great, thanks.
Ooh. Yeah, hi, okay. So now we have Anouk Van Maris, who got her degree in AI in the Netherlands and then came to the BRL, where she has received her PhD in ethical human-robot interaction. She's about to tell you a bit more about that now, so I'll hand over to her. The floor is yours.
Yeah, thank you for that, George. Hi, everyone. Yeah, my name is Anouk. I'm currently a research fellow in responsible robotics for the Robotics project that Alan Winfield talked about earlier in his talk, but that was on track 1, so I'm not sure whether you've seen that. But since he's been talking about the project that I'm currently working in, I will be sharing with you the work I did during my PhD, where I investigated ethical concerns during human-robot interactions. And the outline for this presentation is really quite basic, where I tell you what my research question was, how I investigated it, what my findings were, a framework that I developed based on these findings, potential next steps, and some general conclusions that was drawn from this work. But to give you a little bit of background information, so this was a 3-year project called Socrates, Social Cognitive Robot Agents in the European Society, and it was funded by the European Commission. And in this project, we wanted to investigate the interaction quality between social robots and older adults. And my specific goal and task was to investigate ethical concerns that may impact this quality. So I had to narrow that down, of course. So I decided to focus on artificial expression of emotions by robots. So when they would display emotions. Because there have been some concerns raised in the literature regarding emotional deception and emotional attachment. So emotional deception occurs when a robot would display an emotion and a person believes that the robot actually perceives this emotion and raises false expectations based on this. And emotional attachment would mean that the emotional behavior by the robot elicits higher level of attachment of that person to a robot, which may lead to overtrust and overdependence and may lead to dangerous situations. So these are 2 concerns that have been raised in the literature, but have not often been actually tested whether they are true. So first of all, I wanted to know more about what these concerns actually entail, but I also wanted to ensure that they are actually concerns and we're not being cautious where that is not necessarily required. So the research question from my project was, can artificial expression of emotion by a social robot lead to emotional deception and or emotional attachment? And within the project, we focused on older adults as a target group. So that was also the target group that I focused on in my research. And a bit more general goal of my project was to determine whether we can use human-robot interaction experiments to investigate robot ethics. So the methodology, please bear with me today because I'm trying to summarize 3 years worth of project here. So I have to be general, unfortunately, can't go in too much detail. I do have some publications that you can read if you're interested in more detail. And of course, I'm also happy to answer questions after this presentation. But yeah, basically, I conducted several user studies to determine whether this expression of emotion had a negative impact or any impact on people. And these user studies were either based here in the Bristol Robotics lab, or they were field-based, where I went to people's homes in semi-independent retirement villages. And I also conducted some online surveys. So my whole project started with the development of these artificial emotions, because without a robot being able to display these emotions, couldn't test anything. So I implemented some emotions and tested them online and also face-to-face. And these results were all very positive. So that allowed me to actually investigate my big research question, which big study, which was is indicated with the blue arrow, where I ran a long-term field study with older adults, where I investigated whether deception and/or attachment occurred. But as we know, all user studies have its limitations and are not perfect. So therefore, I also ran a final online survey with over 200 participants to see whether the findings that I got from this really big study that allowed me to answer the research question was also found in the general public, in the opinion of the general public. And all these findings combined, I used to develop a framework that can hopefully help developers of social robots to support the behaviors that they're implementing and make sure that there are as little negative consequences as possible. So looking at this big long-term study with older adults, you see here a room in an apartment in one of those semi-independent retirement villages, with the setup where the participant would be seated opposite the robot. And there would be in total 8 interactions between the older adults and the robot, spread over a period between 5 and 6 weeks. There were always a few days between each session. And I used a lot of different types of measurements because we have some measurements for human-human attachment, human-pet attachment, but nothing for human-robot attachment yet. So we didn't know which one would be best suitable. And similarly, for deception, there is no clear way to measure that. So I tried to use as many different measurements as possible to get rich insights on user experiences. So I used questionnaires. I also gathered people's physiological data. So more specifically, I gathered their galvanic skin response, which is how sweaty a person is, because an increase in that response might indicate levels of discomfort. And I also gathered their heart rate variability, because this could indicate an increase in arousal. And this can be both positive and negative. So then other data would help me to determine whether this increase in arousal was a positive or a negative effect of the interaction. As you can see in the photo, there's also a tripod, because I recorded participants, video recorded participants from the front, which allowed me to analyze their behavior and once again see whether there were maybe signs of discomfort based on certain behaviors that the robot was displaying, and which would support then whether the heart rate variability arousal increase was positive or negative. And finally, I also recorded their speech data. So more specifically, I looked at the pitch and volume of speaking when they were talking either to a robot that expressed emotions versus when it did not, to see whether there were any changes, and indeed which could indicate levels of increased arousal. This study has been presented in the publication mentioned here. And of course, there's many data that I gathered and many useful data, but it should also be noted that there was also quite a bit that I unfortunately couldn't use. So for example, looking at the physiological data, the galvanic skin response did not provide any useful outputs, which was unexpected, because when I tested it with people in the lab here and pilot study, useful values were gathered, but it just didn't apply when used on older adults. So unfortunately, I couldn't use that. And with the behavioral data, I found that there was so much to see in how people responded to the interactions, but this was not necessarily only to the robot's behavior. So their reactions were not only when the robot would show an emotion of happiness, for example. So even though that was really interesting data, it did not allow me to answer the research question, so I couldn't use it for that. So there's many findings that unfortunately I cannot all share with you. So I'm going to share one big one that I think is really interesting. So as I said before, I've been looking at both attachment and deception. And based on people's answers to attachment questionnaires, they were categorized as having low attachment to the robot, medium, or high attachment. And one of the measurements used to investigate emotional deception was the perceived social presence of the robot. This means it investigated to what extent participants saw the social robot, the robot as a social entity, as a living being, because that might be an indicator that if the robot displayed emotions, it was seen more as a living being. And the results indicated that the higher the level of attachment to the robot, the more they perceived the robot as a social entity. And therefore, it indicates that there might be a link between attachment and deception, which was a very interesting finding. And also, it answers the basic question that indeed artificial expression of emotion can lead to attachment and deception, but does not necessarily have to. So as I said before, I decided to run a final online survey based on the results from this big user study with older adults to see how well these findings were met by the opinion of the general public. So I turned my findings into statements in 5 different categories. And what I really liked about this survey is that I provided context to the participants about why these statements were presented. And participants then were asked on a 5-point scale to what level they agreed with this statement or not. And I provided this context as it allowed participants to give more informed answers. In human-robot interaction experiments, we often use questionnaires where no background is provided. So participants may not always understand why a question is asked or misinterpret a statement and therefore give a different answer than they would have when they would have had all this information. So this is how I try to account for that. And I divided the statements that I had in 5 different categories. So the first category is social robots displaying emotions, which entailed whether participants were happy for a robot to display emotions, whether they were comfortable with that. Also the question whether they thought it was deceiving, with an explanation of what this deception meant. And also there were some statements about attachment to social robots and whether that was a good thing or a bad thing. And since the target population was older adults, which is sometimes categorized as vulnerable users, I also decided to put some statements in there on vulnerable users that use and interact with social robots. And what I found really interesting from my study with older adults was that they indicated that they did not have any issues with the robot collecting data if it was for their benefit, to share with their GP, for example. So I asked the general public more about that as well. And finally, deception is often regarded as a bad thing, but it can also be beneficial. There can be good results to using deception. So, for example, when a white lie is told to make sure that a person remains calm. So, therefore, I also included some statements on lying social robots and whether people thought that was acceptable or not. And actually, the main finding from this survey, where 239 participants completed, is that they did not have a clear opinion on many of the things. So on the left, you see a 5-point scale. 1 is strongly disagree with statements and 5 is strongly agree. And overall, for most of the categories, it can be seen that participants actually neither agree nor disagree. And that was also found in the statements, the comments they provided afterwards, where they said, it was very clear what was asked, but I never considered it before, and I really don't know how I think about this. So that is very interesting, because this way at least we can present the situations to people, and I even got some comments from people that it actually got them thinking. So this way of presenting surveys is good for more than one way. which was really interesting. But yeah, there was not much that could be concluded from the findings, how they compared to the opinion of the general public. Interestingly enough, it did appear that participants did not mind the robot collecting data if it were for in their own benefit. So all these findings combined, I tried to put them in a framework, and I named this framework after the project that allowed me to run this study in the first place, Socrates. So it's the social robots and artificial emotions framework. So unfortunately, I cannot show you the whole framework at this point because I'm currently turning it into a publication, but I'm going to share an example with you here. So the framework consists of 5 columns, and the first one of that is components, and components entails factors that may raise ethical concerns. So in this case, that's the population, because vulnerable populations, for example, raise more ethical concerns than other populations. So that is one thing to consider. And then the next column provides a general recommendation. So a general recommendation for the population component is determine your target audience. And then next, some reflective questions are provided, how you can determine your target audience. So a question can be, does the target audience include people with impairments? And this can be cognitive impairments or physical impairments or even both. And then based on the answers to these reflective questions, more specific recommendations are presented. So for example, imagine that the target audience includes people with cognitive impairments, such as dementia. Then the specific recommendation is that the level of impairment should periodically be assessed. Because as we all know, the dementia deteriorates over time and gets worse over time. And so it should be assessed periodically whether the robot's behavior and the robot's functionality still meets the requirements for that specific level of impairment. And finally, there is the final column provides the level of risk that this component indeed is an ethical concern. And for this specific example, the level of risk is gradient as it increases with the severity of the impairment. And in the framework itself, there's many more components. Components can have several recommendations, more than one reflective question, and then each question again has a specific recommendation. So it's quite an extensive framework, and I hope to publish this soon. So please keep your eyes out for this if you find it interesting. And then some next steps on this work. Well, as I said before, the first step to do now is to publish this framework. However, no framework is perfect from the start. So it will also, I would like to test it and see how easily it can be generalized to other robot platforms, other kind of interactions, other scenarios than the one that I used in my studies. And as I mentioned before, not all the measurements that I used were suitable for me to answer the research question. So more additional measurements are required for us to be able to fully understand what the impact of artificial expression of emotion would be. And besides deception and attachment, there are other indirect and unintended ethical concerns that may not be known straight away, that develop over time, which should also be included and investigated. And I would love to be able to turn this into guidelines and standards. I'm currently a committee member in a working group of the British Standards Institute, and I'm trying to include my findings as much as possible there. But yeah, I would like to take that further and broader and get on with that. And an ambitious goal for the future is to maybe even develop a trademark where we can say, if you have this trademark, then the behaviors displayed by your robot have very little negative consequences. And that is something that I would really love to develop in the future. So the very broad conclusions that can be drawn from this work without providing too many details, sorry for that, is that emotional deception and emotional attachment can occur when a social robot expresses artificial emotions, but it doesn't have to. And more generally, human-robot interaction can be used to gain initial insights in ethical concerns that we have for robot ethics. However, the existing measurements that we have are not sufficient for us to gain a full understanding of what these concerns actually entail and what the consequences are. So that raises questions about whether we should focus more on making sure that we are able to test this before we develop the robots further, or whether this should at least be done in parallel. And yeah, thank you so much for listening. I'm very happy to answer questions, and feel free to contact me in any way. And I just wanted to finish my presentation with this this quote from Julie Carpenter, because yeah, I just feel that resonates very well with the research that I do, and I would like to continue this for my academic career. Thank you.
Great. Thanks very much, Anouk. That was interesting. It sounds like a very it sounded very, very thoroughly thought out and very well analysed afterwards. So in developing this framework, I mean, essentially you talked us through your progress there throughout your PhD, and there was a lot, and particularly in the field that you were doing in human-robot interaction and ethics, getting the methodology right and knowing what you can take from it is difficult to get exactly right. And as I just said, I think it sounds like you just had to spent a long time thinking about that and thoroughly analysing it afterwards. So if you were to go again, as it were, to try and have the same, you mentioned a few times you had to study with people, and for a certain way you couldn't quite draw the conclusions that you wanted to. If you could go again and do all this again, would you now feel better equipped to be able to set out your initial set of experiments and gather the data in a way that would be able to answer those questions, or is that?
Well, there's definitely a lot of things that I learned from running these experiments, and how to deal with small things. And also, for example, in the online survey, you always want to make sure that there is the statements are counterbalanced and all that kind of stuff. And I made small mistakes there that I now know how to address. And if I talk about the really big study that I did, then I think it was a great start, but there's always room for improvement. Unfortunately, one of the drawbacks of my study was the number of participants. We put all the effort that was possible into recruiting as many people as possible, but people have to be willing to do it, especially as it takes several not a one-time time to be committed and dedicated. And then with that also came the limitations of the PhD itself. There were the time limitations and stuff like that. So if I would do it again and would not have these constraints, I just would take all the time in the world to actually run the study. I would run it. I ran it twice now to get more participants, but I would actually run it maybe 3, 4, or 5 times to just get that good number of people that would actually give more rich insights, where you could say, okay, this is not an outlier. This is actually something that we can find for real. I also learned about different sensors to use for all the other kind of measurements, but and there's room for improvement there. But at the same time, there's also not everything available yet. So, for example, for the physiological measures, we used a sensor that does really well, but we also wanted it to be very non-invasive for the participant. So it was placed on people's hand, and that's a very sensitive situation for physiological data because there can be a lot of noise there. But there is no non-invasive sensor that doesn't deal with this noise. So yeah, there's many things that can be improved, but there's also things that are really missing that I cannot improve myself to make this a really quality work.
Okay, yeah. Well, again, a very thorough answer, which is, I think, answered my questions. Yeah, so I mean, I can relate to that part of my research now. We're doing, we've sent out a survey, and you know, there's always, in retrospect, I think there's certain things you could have put in to answer the questions that you really want to have been answered within it. And likewise, number of participants, I think you can always bump it up. But it looks like, yeah, like I think I've said, you've drawn some good conclusions from that. Okay, well, yeah, okay, so there are no questions coming in from the live chat at the moment. So I think with that, I think I'll say thank you for your talk.
Yeah, thanks for having me.
Great. So, right, okay, so that brings us to the end of this second morning session. And I think next we're at 12:30. So I think before a lunch break, there is a panel talk over on a different channel, over on a different YouTube channel, about what is the future of robotics, with Arthur Richards, Manuel Giuliani, Sabine Houghton, Praminda, Caleb Solly, who are all from different, who have all taken different paths and probably been thinking about the future of robotics for quite a while. So that should be an interesting talk. Okay, so I'll close this channel now. Thanks for watching, everyone. I hope you enjoyed it and learned something. And thanks again to all of our speakers. That was good. Thank you.